Hey everyone, welcome back to my Calculus 2 series. In today's lesson, we're going to be going over absolute convergence and the ratio test. So let's say we were given a series like this, right, where it spanned from n equaled 1 to infinity, and let's say the term was just a of n. Now, what we can do is we can also consider this other series right here that we'll get by basically taking the absolute value of a of n. So this series right here, well, it would be like a of 1 plus a of 2 plus a of 3 and all the way to whatever. And then this series right here, well, that would be absolute value of a of 1 plus absolute value of a of 2, and then obviously like so on. So it'd be the same terms, however, the only thing that would change is now we would get the absolute value of each individual term. And now this, you'll see how this is going to tie in with absolute convergence, but this is actually very useful. Tying this into absolute convergence, basically, if we are given this starter series where it's just the series of a of n, we just want to sum up all these terms. And we call this series absolutely convergent if the absolute value, like the series of those absolute values, is convergent as well. And like I said, it's just this other series right here where we basically take the absolute value of each term. So if that series is convergent, then we call the starter series, this one, we call it absolutely convergent. And I'm going to later on explain why it helps if a series is absolutely convergent versus just convergent. There will be a distinction between the two, but we'll get to that later. And obviously, if the series is not absolutely convergent, meaning that the absolute value, like the series containing the absolute values, is not convergent, it's divergent, well, then we say that the original series is called conditionally convergent, provided that it is also convergent. So if this right here is divergent, however, this right here is convergent, well, in this case, we're going to say that this is conditionally convergent. However, obviously, if a of n is also divergent, well, then we just simply say that this series is divergent. We don't even care about the absolute value of those terms. And I said, obviously, there is a distinction between absolute convergence and just convergence. Obviously, because absolute convergence means that, well, additionally, like added on to just being convergent, well, the absolute value of each term, that series is also going to be convergent. So it's kind of like a step further. And basically, being absolutely convergent means that, well, the original series is convergent. And I know this seems very obvious because I've said it a couple of times now, but I'm going to show you examples and I will show you why it's a lot of the times easier to compute the absolute value of a series rather than to find like whether the plane, like the original series, is convergent or divergent. So a lot of the times we'll be taking the absolute value of the series, finding whether that is convergent or divergent. If it's convergent, well, then we can say that the series is absolutely convergent. And if that series is absolutely convergent, well, then we can say that the original series is convergent. So we can see how we're going to apply this absolute convergence in this example that I'm about to give right now. So we are given this series, and looking at it, it's pretty complicated. I wouldn't, if I didn't know this method, I wouldn't really know where to start with it. So obviously we're going to use the absolute convergence method, and we're going to try and find whether this right here, the series of this, is going to be convergent. So, well, let's start breaking this series down. Well, we can see, by the way, I'll add these bounds right here. Obviously, the denominator right here is always going to be positive. So we can kind of bring it outside of these absolute values. And the reason it's always positive is because it's being squared. So there's no way we can have a negative value in the denominator. So basically, this is going to be equivalent to the series, but instead we're going to remove the absolute value sign around the n squared. And now, well, if we look at this right here, so cos spans from the original cos, it spans from -1 to 1. The values are in between somewhere there. However, if we throw the absolute value sign around it, well, now all of a sudden it spans from 0 to 1. So we can say that this right here, well, it's going to be less than or equal to 1. And now what we want to do is we kind of want to use those comparison tests that we've learned about before and compare this series right here to a much simpler series that will be this. And we know that this series right here is actually going to be greater or equal than the series that we're currently working with, which is the absolute value of cos of n over n squared. And again, the reason for that being is because, well, the denominators are the same. However, this numerator, as I've shown in this block right here, will always be greater or equal than the numerator right here. So that means that this series here would be greater than or equal to this series right here. So now let's find if this series right here is convergent or divergent, and it's pretty easy to tell by now. This is a p series with p equal to 2. And because p is greater than 1, well, that means that this series is convergent. And if this series is convergent and it's in a sense a larger series, well, that would tell us through the comparison test that this series right here, the smaller series, is also going to be convergent. So this series is convergent. And now that means that, well, this series right here, the one that we initially took and we kind of simplified it to get to here, well, that would mean that this series is also going to be convergent. And well, if the series of the absolute values is convergent, well, that means that the starter series that we got is going to be absolutely convergent. And if it's absolutely convergent, well, then we can easily conclude that this series is also going to be convergent. So through this example, you can see how we've applied multiple concepts, but most importantly, we have used this absolute value to get rid of this cosine, which honestly, I wouldn't even know what to do with if we didn't have this method. So you can see now how we can use this, taking the absolute value of the series and to greatly help us. We basically, all we need to do is we take the absolute value of it. If that series is convergent, well, then we can say that the starter series is absolutely convergent, and inherently that means that it's convergent as well. Building on top of that super useful absolute convergence stuff, we also have a really useful test, and it's called the ratio test. And if there was one test that I would stress, like understanding and knowing, it's the ratio test, because it's super applicable. It'll help us a lot with the future series that we're going to be dealing with, but this test is super useful. It can be applied in a number of scenarios. So I suggest that you pay attention and kind of understand it and know about it. It's basically a buildup of what we had about the absolute convergence. So there are 3 cases for the ratio test, and the first case is that, well, if we have this series right here, that just basically it's just the sum of all these terms a of n, and if we take the limit of the a of nth plus 1th term and divide it by a of n, and then we take the limit as n approaches infinity, we're going to get this number. We'll call it L, this limit. And if the limit is going to be less than 1, well, then we can conclude that the series is absolutely convergent. And once again, if we conclude that the series is absolutely convergent, then we can conclude that the series is also convergent. So super useful. Now, if that limit right here, L, is going to be greater than 1, or it's going to equal to infinity, well, in that case, the series is going to be divergent. And again, you can clearly see super useful. There's no really like complex calculations needed. You'll kind of see how it's just us simplifying stuff like these 2 terms. They'll have a lot of common factors, and it'll be pretty easy to cross them out and kind of just simplify and then calculate the limit of that. And then from there we can conclude about the series itself, which is going to be super useful. And then lastly, if that limit is going to be equal to 1, well, then we say that the ratio test is inconclusive, and we'll need to kind of rely on all of the other tests that we've learned before. So let's grab a look at this right here and see how we can apply the ratio test with absolute convergence. So this series right here is obviously an alternating series. However, I don't know much about, well, what bn plus 1, which term is greater, n plus 1, or b of n. Like, I wouldn't really know that. Also, the limit would kind of be a little wonky to compute. So I'm just going to go ahead and turn to my trusty ratio test. And again, I mentioned this, the ratio test is going to help us in a number of scenarios. So I suggest if you don't know how to approach something, try the ratio test. That's my kind of go-to test if I don't know how to solve the series. So let's look at it. Well, the ratio test requires us to take the limit as n approaches infinity of a of n plus 1 over a of n. And in this case, we need to find two things. What is a of n and what is a of n plus 1? So a of n, well, that's simply just going to be like this term right here. So it's simply just going to be minus 1 to the power of n times n cubed over 3n. And then a of n plus 1, well, that means that for every n we see, we just plug in n plus 1. So it's going to be minus 1 to the power of n plus 1 times n plus 1 cubed over 3 to the power of n plus 1. And we can see wherever we saw an n, we just plugged in n plus 1 instead. And as you can see, there are a lot of common terms in between these two kind of values. So we can see already how they will be crossing out once we start dividing them. So let's go ahead and find what a of n plus 1 over a of n will be. A of n plus 1, I'm going to start off with that. And again, I'm going to avoid, because this is a fraction, I'm going to avoid writing this kind of like layered division where we get a bunch of these layers. So instead what I'm going to just do is I'm going to write a of n plus 1 times 1 over a of n. I'm just going to write it like this instead. Let's start off with a of n. A of n is minus 1 to the power of n plus 1 times n plus 1 cubed. And then all of this is going to be over 3n plus 1. Now we want to multiply 1 over a of n. Basically, we're just going to flip this fraction. So it's going to be 3 to the n over minus 1 to the n times n cubed. And now we can already see how this term right here and this term will cancel out, leaving us with just a single minus 1. And then we can see how this term right here and this term right here will cross out, leaving us with just a 3 over here, because obviously this was n plus 1 and this was just n. So now this has simplified into minus 1 times n plus 1 cubed over 3 times n cubed. And we can see how simple this already is. Now what I'm going to do is I see these and they're both to the power of 3. So I'm going to combine them and put them both basically to the power of 3. So we're going to get minus 1 over 3. And then over here we're going to get, actually I'm going to write it like this. So we're going to get n plus 1 over n cubed. And this is now what this term represents. So now what we said we were going to do in the beginning was we were going to take the limit as n approaches infinity of this term. So let's take the limit as n approaches infinity of this term right here. And obviously we can bring out minus 1 over 3 out of this limit because it's not dependent on n. So there we go. I have solved this limit and I have found that the L value, or the value of the limit, is going to be minus 1/3. And if we go back up to our ratio test, well, what can we see? We can see that if L is going to be less than 1, then the series is going to be absolutely convergent. So in this case, we can conclude that the original series that we started with, this one right here, well, this series right here is going to be absolutely convergent. And what does that mean if it's absolutely convergent? It also means that it is convergent. So you can see how over here we have found whether the series is convergent or divergent by using this method. And it looks like a lot of steps, but it's really not. Once you get pretty proficient at this, you don't really have to write down like this step right here or this step right here. You can kind of skip to here and then you will just basically figure out what they kind of simplify to and then take the limit of it. And the limit of it is pretty easy most of the time. It's something as simple as this. And obviously I showed the solution in this case, but you can kind of see that this limit is just going to equal to 1. So you can skip even like these 3 steps and just know that it's just going to equal this outside factor. So yeah, that's it for this lesson on absolute convergence and the ratio test. And essentially they're both really, really useful tools to help us determine whether the series is convergent or divergent. And again, my suggestion is if you don't know how to approach a series, try the ratio test as your #1 go-to sort of thing. If this video has helped you out at all, please like and comment as to what I helped you out with. Like usual, if you're new to the channel, please like, comment, and subscribe. It's greatly appreciated. And yeah, I'll catch you guys in another video.